Okay. Well, thanks a lot for having me today. I know um, it's a little like too late or too early here in this time, but it's really great for me to join your event because I'm really excited about what your team is doing. But at the same time, I feel bad for not being able to be there in person because I really wanted to go there. But anyway, I really appreciate for hosting me remotely. I hope this goes well. Today, I will try to share some maybe potential future directions that I think in your speech codecs, but maybe with a little more on emphasis on the communication applications. So just wanted to introduce neural speech and audio coding in general in comparison to the traditional codecs. So back in the days before we start to use machine learning, deep learning for coding, this was like the typical graph people looked at. For example, there's this, speech codecs, like the green line, that are standardized for speech communication most of the time. They work pretty well in at low bit rates under 10K sometimes, BPS, but its performance usually saturates at around 24K. Around this was the high bit rate for speech codecs. And at the same time, there's this other codecs called audio codecs that are designed more to compress the audio signals. They work really well at high bit rates and they sound great, but at the same time, at the low bit rate, its performance for especially for speech isn't as good. So when we develop, deep learning based codec, or any machine learning based one or data driven methods for coding, we want that what we want it to be better than these existing codecs, of course. Although it's not as straightforward as we think. I can maybe talk about a little more about it, but we all know that it's not that easy. Um, but anyway, if we can, train a neural codec in this way, then they're really like versatile in the sense that since it's based on neural networks, we can sort of harmonize the neural network based codec with the other neural network based applications such as speech enhancement, ASR, TTS, or these days LLMs, because they are really versatile. And we can sort of start to see the code as some sort of a feature. That's very nice. So in order to do this, we need to work on a lot of limitations, maybe. For example, the notable issue would be complexity and delay of this codecs. Because, if you think about this, speech and audio codecs, they do have their own complexity, of course, but compared to the neural codecs, the complexity is really incomparable. So how do we handle that? And at the same time, when you train the neural network-based codecs, it's not too straightforward to come up with the loss function that makes sense to, human listening tests, for example. So that's another thing we need to worry about. And scalability is another issue because, these codecs, for example, speech and audio codecs, they are bitrate scalable, so they can sort of change the bitrate depending on the bandwidth of the network that's available at the moment. So things like that is sort of open questions and challenges when we develop neural networks for coding, especially for communication applications. So if you think about audio coding or speech coding, it is pretty straightforward as a neural network. Before that, back in the days when people developed traditional codecs, it consists of multiple sort of blocks that people come up with, and then it's a combination of them. For example, suppose you feed a speech or audio signal to your encoder, then the encoder consists of multiple modules in there, and then the encoder turns the input signal into the bit stream, the code, and then it's either transmitted or stored, and then it's sort of decompressed by using the decoder, which also consists of multiple modules in there. And then hopefully the result after decoding is similar to the input, That's what we want. But how do we actually judge the quality? Back in the days, people just listen to the signals because people know that it's not always possible to rely on some objective, metrics there anyway. Um, so, after listening to the input and output of the codec, and then they find something is weird, then the researchers or engineers, they go back to the models that they developed and then maybe adjust the parameters in there, or switch the model into different ones. So that was sort of a standard process when people developed traditional codecs, and it took 40 years basically to develop this so-called state-of-the-art communication codecs. But in the deep learning era, we can turn this into some autoencoder. So basically, you feed the input signal to an encoder, which now consists of multiple neural network layers or neural network models, which is parameterized by some, model parameters, and then at the same time, it also produces some code, and then the code will be decoded by another neural network decoder, which will produce the output, and the input and output can be compared, of course, by using subjective methods. But at the same time, we can sort of come up with the loss function, which will be backpropagated to update the network parameters. So this process sounds like an automated process, and if we have enough data, we can sort of develop this kind of system pretty easily, because differently from the supervised method or supervised learning tasks, we don't need to label these signals. The input and output are the same thing, so it's the autoencoder. So we just have to dump a lot of data to the neural network and then update the model accordingly. So autoencoders for audio coding is not a new idea, actually. For example, this is like the drawing that I did about 16 years ago. I was thinking that, for example, the spectrogram, MDCT or STFT or whatever, that can be, if you just select a few spectra out of it, then it becomes a matrix. And then back in the days, matrix factorization was, very popular and easy to use. So we can sort of come up with the dimension reduced version of that by doing some matrix low rank approximation. Basically, you can use PCA, NMF, or whatever dictionary learning algorithms to do this, and then you can basically recover the input matrix, the spectrogram, by using this A times B kind of inner product. So this sounds like a working system, and I even wrote a paper, by the way, in 2008. This was me back in the days over here. It was like really fun to work on this, but I sort of gave up on this back then because I was able to see that the matrix factorization can do some approximation, but as for the bit rate, I wasn't able to compete with the existing systems, and it also had a lot of issues that I mentioned, like how to judge the subjective quality of this and so on. And then fast forward, now we can do neural network-based codecs, which is sort of, to me, like not a multi-layered version of these autoencoders. So we are facing a lot of different neural codecs these days. But from the communication codecs perspective, these are sort of the attributes that we expect from a codec traditionally, such as low bit rate. Nobody likes a super high bit rate from a codec, but at the same time, when it's for speech communication, the latency shouldn't be long. The algorithmic latency shouldn't be too high, because then people will hear the delay when they are on the phone, so it's not that nice. So the latency has to be low enough so that people don't realize it. Maybe 20 milliseconds or something like that. But at the same time, we are talking about running these codecs, encoder and decoder, on the device. So unless the device is super large, or it's powerful enough to run GPUs, we need to worry about the complexity of the codecs because otherwise it's going to drain the battery. It's not just about speech communication, by the way, because the codecs, audio codecs, can be used for music streaming, for example, as well. So suppose you're in the airplane and then you're listening to some music that you stored on your phone. You want to listen to it maybe for 8 hours or something. And what if the battery drains after listening to music for 8 hours? You don't want to see that. So complexity is another issue. And at the same time, we want the decoded signal to be high quality, or in other words, the reconstructed signal out of the codec, decoded version should be as similar as possible to the input perceptually. So that's another thing we want. And at the same time, it should be robust to the network environment. So if there's any packet loss or something like that, then that has to be recovered as well. But what else? These days, codecs are also used for some other downstream tasks, as we might have seen today a lot. I'm sorry, I missed most of them. But what if we just want to use the code as a representation feature for the other downstream task? That's another thing we want to think about, which is actually something that the traditional codecs are missing, and that's why we work on the neural codecs these days. So, there are different kinds of codecs and many different codecs developed very recently. So if I just roughly try to sort of categorize them into different versions. So this kind might be some models that are relying a lot on the decoder's complexity. I'm not going to go over all of them, but most of the time they don't care too much about the quality of the code or how we get the code. The encoder is really simple in this case. But they can do whatever funky things there, like using generative models or things like that. And eventually, there's a trade-off between quality and complexity and bitrate in this case. More balanced versions are encoder-decoder, like autoencoder setup, where the encoder is learning some features in the middle, and the decoder is using the feature to recover the original signal. Typically, these are based on the CNN encoder-decoder architectures. In that regard, they are more flexible structure-wise, and the complexity is more moderate because they don't have to be too large. And it's versatile because the encoder representations can be used for the other downstream task, and then the downstream task can use the decoder to recover the original signal. And then there are more encoder heavy models that are good for downstream apps. Although if you want to think about this as a communication codecs, they might be a little too large to run in real time, for example. I just realized that semantic codec, from my perspective in this figure, is a really unique one because it is actually using some diffusion model as a decoder, so it can be seen as a decoder heavy model, but it cares a lot about the feature quality as well. So it's using some proper decoder. So that's why maybe it works really well. These are sort of conditions we want to think about, like back in the days when we train a neural network codec, like psychoacoustics. People use a lot of this in traditional codecs. And how about residual learning or predictive learning or generative models? These are sort of, I think, the key to achieving higher performance. And what if we want to do some sort of, analysis of mixture audio? Then we need to do source separation and coding at the same time. I have a paper about this as well. Actually, how do we actually see the foundational models as an encoder? Or how about using language models on top of codecs? How about personalizing the codec for some personal, speech communication? These are sort of really nice things to think about as a codec development. So one thing I'd like to introduce today is, for example, predictive coding. So suppose that you have a code. We start from some, predictor, maybe some RNN model like GRU, which sees some past frames, and then it wants to predict the current frame out of it. Why do we care about it? For example, suppose you have an encoder, and instead of sending the code to the decoder directly, we actually try to predict the code by using the previous code vectors in the past, then during the training time, we can sort of try to learn the residual signal by comparing the prediction out of the existing code. Then what that means is that the residual signal now can be quantized and then sent over to the decoder instead of the code. So code here is, by the way, not quantized as it's a floating point code. So why do we want to do that? It's well known that the residual signals are with the lower entropy, so you can reduce the bit rate even further by doing so. And then on the in the encoder side, we are gonna actually just harmonize the residual signal back again with the prediction to recover the original code vector, which is not perfect, but it's gonna be a really nice reconstruction. So on the decoder side, we take the residual signal and then merge that with another predictor, which is the same predictor, by the way, running on the decoder side. And then it does some harmonization of the residual signal and the prediction to recover the code. And it just keeps doing this. And then we finally use the code to run some maybe vocoder like LPCnet or any other decoder to convert this into the waveform signal. So I wanted to introduce the importance of doing something in the latent space by, for example, doing predictive coding and residual learning, because that way we can dramatically reduce the amount of information we need to send over to the decoder by working on the residual signal. And then if you compare this kind of a predictive coding result with the other models that are sort of similar baselines, we can see that the performance is better, although the bit rate is lower. So this is sort of how to say my emphasis that I wanted to share today with folks, that we can sort of try to play around with this latent representation, because it's really nice and important to do that for speech communication or actually any other coding applications as well. But then this makes us think about what would be the best way to learn this kind of latent representation given what's happening. So my ideal thinking was something like this. We can assume that there is a autoencoder like this one that takes the input and then it converts the input to some latent representation, and then there's a decoder that converts it back to the original signal domain. And this encoder and decoder pair, they don't do any quantization, by the way. And then they don't have to do some dramatic dimension reduction as well, because this is not a codec, this is an autoencoder. It just learns the feature. And then since the feature is still relatively high dimensional, and then it doesn't do any quantization, the reconstruction must be near perfect. That's something we can imagine as a sort of ideal autoencoder, and it's usually this autoencoder because it didn't go through any quantization, so bitrate must be super high. So it's useless in that regard. But at the same time, we can also think about the typical neural codec, such as encodec or DAC or whatever other autoencoder based codec, which does the quantization in the middle, and hopefully it might have done some dimension reduction as well, because if you reduce the dimension, you can sort of also reduce the bit rate accordingly as well. So it's very typical to reduce the dimension and at the same time apply quantization on it. And then, what that means is that we need to train a corresponding decoder accordingly so that the input and the output are as similar as possible. And this is tricky because we want this H, the quantized H, to be super low dimensional and super low bit rate. So it basically goes through a lot of transformation and it's injection of quantization error, I would say. So my proposal is like, how do we combine these two ideas? Because this is used for typical codec, we want to use this, but the quality is not good. And this one on the left is ideal, but we cannot use it because the bit rate is too high. So what if we just take the encoder part of this discrete codec, and then the decoder part of this continuous codec, and then somehow merge them together. What it means is that we need to merge H and Z somehow, and then they have to be in the same representation, which is impossible because they are not in the same latent space because they are learned differently. One goes through quantization and dimension reduction, the other one didn't go through anything. So we need to do some upsampling and dequantization at the same time. How do we do that? We can just try to do it, but it's not that easy. So because, just trying to learn some upsampling and dequantization at the same time, it just sounds like a codec. So we can get some help from the generative model by using latent diffusion model. That's why we call this LaDiff codec, which is latent diffusion codec, and I like it because it sounds like French. So basically, we convert this. We think that there is a diffusion process that converts this continuous code into some noise, and then the reverse diffusion process will basically convert it back to the original space by conditioning the denoising model by using the quantized code. So if you do this multiple times, then this should sound good. So that's why it's called LaDiff codec. And then compared to the baseline model that we were using, we were able to see that I don't know if you can see it over there, but the user aliasing artifact of encodec is gone and it sounds much better. I'm not going to play the sound because it looks like it's not audible from there. But we have a website for this, so you can check that out. One thing I'd like to introduce here is that, for example, the left continuous codec now can be with larger dimension as well. So instead of applying the typical strides, a lot of strides at every layer, we just apply one stride in one layer. That actually sounds really well. And we don't want to do this if this was a typical codec, because then the dimensionality is too high and it's going to increase the bit rate by a lot. But we don't care about it because we can get this representation for free by using the generative process. And then if we did the mutual test and compared to encodec, it sounds much, much better. And DAC, actually, we just used the public DAC checkpoint for this, which wasn't trained on our data set. So maybe that's why it doesn't sound good. But anyway, it sounded better than DAC, which wasn't fine-tuned on our data, by the way. So it's sort of unfair comparison. I wanted to share some example here, which might not be audible for you, so I'm not going to play. But what's really funny here is that if we use this codec with some relatively low bit rate, then it starts to, show some hallucination behavior. So it flips the phoneme from one to another. This example, original word was serve like serving the table at the restaurant. But with this naive version, it flips the phoneme and then it sounds like serve instead of serve. So we had to do some kind of extra training optimization tricks here and there, which we explained on our paper in detail, but we could sort of remove that. But I thought it's really interesting because this generative process introduces hallucination, which is actually a deal breaker as a speech codec. Yeah. And then I will move on to my other topic, which is about personalized speech codec, which is actually really interesting for me because it's only possible using neural codecs. So let me try to explain this from the manifold learning perspective. So suppose that you have some sort of a contaminated code, which is off from the original speech utterances manifold. So the goal of the decoding job is to go back onto this original manifold by using some neural network decoder. But if the decoder is compressed and small, because we care about complexity and everything, then the reconstruction might not be as detailed as the original manifold. So the recovered manifold will be some sort of a smoother version, which is not as good as the original signal. So that's why we hear some, a lot of reconstruction noise if you do this. So the idea here is that if we focus on a particular talker instead of everybody, then we can construct a new manifold that's sort of personal. Then the personal small subset of the clean speech will be maybe, smoother as a manifold, and maybe a smaller decoder can still do a great job because the problem is now simpler, right? So that's basically the idea. And then it means that the less powerful motors can still work as a on the sub problem. So the idea is can be represented in this way as a codec. So we feed the input signal to the speech encoder, and then it goes through some sort of a speaker encoder, which learns the speaker embedding out of it. And then speaker embedding will be classified into different classes. And then at the same time, the input signal also goes through this, the regular transencoder, which is the encoder of the codec. And then when we use the encoder, we will choose the best encoder for the speaker. How do we choose that? We are going to use the classification result that we just did over here. And then it means that each speaker gets assigned to the best encoder that's specific for that talker. And then, the bit stream is generated from the encoder, and then the bit stream will be decoded on the receiver side. And same thing happens. We're going to use the personalized decoder, which is again using the index information that's coming from this classification. So the reason why we do this is that if we pre-train all the speaker-specific encoders and decoders, then they are going to be much smaller and works really well for that particular person. So in that regard, we can sort of reduce the inference complexity by a lot by only using one of the small encoder and decoder pair. And if you look at the speaker embedding visualization, it's sort of, if suppose that you just group the speakers into two groups, then it's obvious that it's following some gender information. So it means that it's doing some semantic classification, actually clustering, I think. As for the four speaker case, it's hard to see what's going on, but I can see that some clustering is happening in the speaker embedding space. So we're going to rely on this sort of speaker groups as a way to personalize the codec. And then finally, as for the baseline, by the way, we're using LPCnet. I'm not going to delve into the details about LPCnet, but anyway, we love LPCnet because it's low bit rate, but at the same time, the encoder is really, really simple. It doesn't have a neural encoder. It's using codec 2 type of very simple traditional code. And then the decoder is relatively heavier, but it's still very simple. It's just a couple of GRU layers happening here. And then instead of relying on the sending the LPC residual as in the typical speech codec, it just synthesizes the LPC residual, which is kind of merged with the LPC prediction so that it can do better decoding. And it works really well given its super low complexity. So if we apply this personalization idea to the LPCnet, then we do the same classification, but the encoder, LPCnet doesn't have an encoder, so we just use the generic DSP encoder, and then we only personalize the decoder part, which is good enough for us. If you look at the performance, we can first see that the blue LPCnet baselines, the bigger LPCnet baseline is better than the smaller LPCnet. So if you do just compression by reducing the model size, the performance degrades, of course. But after personalization, we can improve the performance in both cases. So this is like really great because we don't have to increase the bit rate, but we just get the free performance improvement by doing the personalization. And what's interesting here is that the smaller model gets better performance boost by doing personalization. And then finally, if I compare the small personalized model and the large baseline, which is not personalized, the performance is kind of neck and neck. So we can say that small personalized model is on par with our large LPCnet, and it means that we can do some model compression without losing the performance sound quality of the codec. So as a recap, we know that neural speech codecs are very successful in terms of coding gain, and then audio codecs are getting there these days. But at the same time, we need to worry about deep learning's typical computational complexity because as speech and audio coding are typically used for real-time communication or streaming applications. So it has to be sort of low complexity, low delay, and we still need to worry about those typical issues as a codec. And then foundation models, speech foundation models, audio foundation models, they are good in the sense that they are learning nice features, but they are particularly heavy than the codec specific architectures. So that would be something to think about as well. And then we know that predictive models, residual learning, and generative models usually help codec. And then I also showed that the personalization is a new concept, and then it helps a lot. Although traditional codecs cannot really use this kind of concept, so that's why it's sort of cool to me. And then neural speech and audio codec is versatile. It can be combined with other applications, as you might have seen today a lot. And then from the feature learning perspective, it can provide some discretized features for the downstream tasks. But again, if you want to do this like in real time and on the device, that's we still have the same typical challenges we need to resolve. Yeah. Um, Jans Kogeland at Google and I recently wrote a small review paper, which is comparing the DSP codecs and the neural codecs from this communication perspective. So if you haven't checked it out, please go ahead and check out, because it's actually pretty interesting comparisons there happening. And then, yeah, thank you. By the way, one advertisement, these are the students who are working on neural codecs these days so far, and they're on the job market. So if you have any job for them, just let me know. Shoot me an email. Thank you very much.
Thank you, Professor Minje, for the very great talk. Any questions from the audience? Yeah.
Okay. Hello, Minje and Hongyi. And my question is about the personalization part. So it's very interesting that you show that the personalization can improve the performance. I have some idea. I wonder you have tried, or I want to know your opinion. So first of all, besides personalize for different speakers, it looks like you can also personalize for different types of audio. So so you can have a music decoder, speech decoder, and audio decoder. This is probably one variation we can consider. And another thing probably we can also consider is for different person, they can probably still share some parameter. They have some person-specific parameter, but also some general parameter. In this way, the whole model is more like a mixture of expert, actually. Like you use the classifier to control the mixture of expert, and this can be another way to do personalization. So I wondering whether you have any comments, or whether you have tried any similar direction. Thank you.
Yeah, thank you very much. It's a very good question, actually. So I did this actually for some other task earlier. Before this, I wrote several papers about speech enhancement, personalized speech enhancement. And I tried things that are similar to what you just said. For example, it's a speech enhancement model, but instead of personalizing to the speaker, it's kind of customizing to different types of noise. So you could, with this similar structure, but in the mixture of local expert structure, for example, the local experts are handling different noise types, for example. So if the surrounding noise is airplane noise, then you use this local expert, and if there's a background music, then you use this other local expert. So that's something we can think about, or we can variate this by based on the SNR of the input. So we can do all sorts of different things there. And in that regard, yes, we can do this for speech codec as well. Actually, we are working on a audio version of this by trying different music genre and then turning this into a mixture of local expert version. So that's sort of a very good idea, and we are working on the music version. And as for the mixture of local expert idea, by sharing some features between speaker groups and so on. We haven't tried for this paper, but for the other, speech enhancement versions, we sort of tried that. And as you say, it works. One thing though here is that I don't know if I should. Oh yeah, so we did learn the speaker groups here, and instead I said it's personalization, and I might have confused you by saying this. It sounds like everybody has his or her own codec specialized for that speaker, but actually what happened here is that I grouped them into speaker groups, and then each group has a specific codec. So in that regard, I'm kind of doing that, but I'm not really sharing the local experts between the groups. So which is something I can do in the future. But yeah, they're actually really good ideas. Yeah, thank you.
Yeah, thank you very much for the insightful answers. Thank you.
Yeah.
Yeah, any other question from the audience? Yeah, I have one question. Actually, I listened to the codec from Haizi. The quality is pretty good. My question is that the diffusion will bring very, very good quality, but the latency is kind of a problem. What do you think for the future work for that diffusion based?
Yeah. So the Latent codec is actually the first codec that I developed without worrying too much about complexity. Before this, I developed some sort of very small CNN codecs back in the days. They are like really, really small. It's like 0.5 million parameters, for example, or even lower than that. So they didn't sound good. They sounded maybe as good as traditional codecs, but not better than them, because I was worried too much about the complexity. So with this Latent codec, I'm like, okay, let's give up the complexity and then let's try to make it sound good and let's see what happens, like other people are doing. And then, like you say, it sounds good, but as a return, since it's a diffusion model, it has to go through multiple, reverse diffusion sampling process. So I wouldn't say this is good enough as a communication codec, but I didn't delve into that part today. But actually, the algorithm Heise came up with is midway infilling, which is actually using much fewer number of steps. And we verified that we don't need even like 100 steps to do that. So in that regard, although it's a diffusion model, there's a chance that we can even lower the number of steps. There are better deep learning people out there, so they can try to reduce the number of steps even further. So that although it's a diffusion model, if you don't have to run it like too many times, then it's still not too complex. And by the way, this might not be the algorithmic delay. If the computer that's decoding this is good enough, then we can still do the real-time processing. So it's not actually introducing too much algorithmic delay, I would say, although its complexity might be higher than the other models that are not using diffusion models. So yeah, that's a valid concern that diffusion model is not good for communication codecs, but I believe that there's a way we can even lower the number of steps than this.
Thanks, Professor Minje. And any question from audience?
If there's no other question, probably I can ask another one. So my question is for the large diffusion codec. Is it fair to say this codec is used the diffusion model as a decoder? But I think there's still some difference, because besides the diffusion model, you also have a fixed continuous decoder. So my question is how important it is for this continuous decoder. If someone directly trained the diffusion model as the decoder, can they get the similar performance to large diffusion codec, or the whole design, the diffusion model plus a fixed continuous decoder is very important?
Yeah, where when we first developed this, Heise and I had a lot of like discussion about this, and our idea was let's use diffusion model as a decoder, because otherwise other people are going to do it anyway. Let's do it quick and do this. And of course, the first idea was to use the diffusion model directly as a decoder, and then synthesize the waveform directly. But we learned that that way we can do some. I mean, then the decoder relies too much on the diffusion model, because all the quality and everything should be directly related to the diffusion model's quality, and maybe the diffusion model has to be large, and then we need a lot of steps to get the realistic synthesized audio. So in that regard, we felt that doing diffusion in the latent space as a latent diffusion model is better, because compared to the raw waveform, still the Z space is much lower dimensional than that, and at the same time, it's a trade-off, by the way, because the continuous decoder up here is not perfect. So the result is, although very good, it's not perfect reconstruction yet. So there's a trade-off, but at the same time, we figured that in this way, we can sort of find the balance between the reliance on the generative model, the diffusion model, and the complexity related to that by offloading the complexity of the diffusion model to this continuous decoder, which is sort of deterministic once it's trained. So I think we don't have any sort of subjective test that compared it, but we found that this is much easier to train the model, and then we can get the nice performance without increasing the complexity by too much. Yeah, I'm sorry, I don't have any evidence because it's just all the internal comparisons. But yeah, this is what I think. I'm pretty sure that this is much better than the running the diffusion model directly to synthesize waveform. Yeah.
Thank you very much for the answer. This is very reasonable. Thank you.
Yeah, thank you.
Okay, so I think due to time limitation, we still need to end the session here.
Yeah.
Let's thank our speaker again. Thanks, Professor Minje, to stay up so late to give the talk. Thank you very much. Thank you.
It was my pleasure. Thank you very much.